Hello and welcome to the session. In today's session, we will be discussing about the program, the course in fact, the subject MCS 12, Computer Organization and Assembly Language Programming. And I'll try to give you a brief roundup of this particular program. We have covered 9 sessions on this particular, not the program but the course. We have covered 9 sessions on this particular course. However, let us put all the information about this particular course into one place. So I just want to discuss with you how exactly this course is, what are the various components of the course, and how you can go about doing this particular course. There are 9 sessions, as I told you, which are already there about this particular program, this particular subject, and those are on different topics, starting from basic computer to we are moving to the central processing unit and assembly language programming. So what does this program cover and why it is so important for you to do this particular course? Well, if I look at the construction of this particular subject, what you see, we start with basic computer organization, right, and go on to discuss about the number representation, and thereafter combinational circuit and sequential circuits. Now, this in itself is a course in many universities at BTech level or at different levels, right, which is with the help of a digital design. This kind of a course is taught, where the logic circuits and logic as well as flip-flop and all those combinational and sequential circuits are taught, right. So this in itself is a course at certain places which tries to teach logic. Here our objective is not to teach you complete logic, but to make you comfortable with the circuit designing a little bit, so that you can appreciate like how those circuits and how those things can be created, although we will be dealing with the simple circuits. But then in the industry, or suppose you go on to join an industry of that kind, then you really need to go through these kinds of courses in detail and learn more about it. However, this is the good starting point for you. Whatever we have covered in this particular course is a good starting point. Then we have talked about the memory organization and input-output organization. Well, these are the essential requirement of any computer system. The memory requirement, basically, if I take you to computer organization course, like computer organization always talks about, in fact, computer organization and architecture always talk about the instruction sets, right? So somewhere down the line, when you are dealing with the instruction sets, somewhere before you go to the instruction set, what you need to know various components and how they interact, and what are the importance of different components, how these technologies work, right. So these are the discussion as far as we have done in this particular course. So basically you can cover some components as well as the organizational component in this particular course, and then we go on to discuss about the central processing unit, where the micro instructions etc. were talked about in detail, and finally there is a unit on, there are on the assembly language programming. In addition, we have many more things. So let us discuss each of these blocks in more detail, so that you can appreciate what exactly we have done in this particular course. So you can imagine that this course gives you tremendous confidence, as well as this course talks about the internals. So the course which talks about the internals will definitely help you in programming, it will definitely help you in understanding concepts of operating system, and it will definitely help you in designing low level software, specifically if you are interested in designing compilers or those kind of compiler writing or other kinds of things where low level programming is essential. So this is the course which is going to give you tremendous confidence. Some of you may go on to do, later on go on to do some hardware description also. So hardware description languages, once again the starting point is the logic gates etc. only, right. So you know all those things, and you can utilize all those things in this whatever you learn from this particular course. Now, if we look into block 1, the unit 1 and 2 basically focus on some aspects like von Neumann architecture. Now, this being the first architecture, and still very one of the popular architecture, although there are many newer architectures have come into existence. So it is in fact architecture which basically defines what computer units consist of, and all of you know what computer consists of. These, I mean, the central processing unit, the input output, and the memory, right? So basically these are the components, but not just these components, but how they are connected, interconnected with each other, and that is the main hallmark. Today you might be having very advanced systems where multiple connection paths are there between the CPU, the memory, and the input output units. But once again, all these parts are going to be very expensive. Circuit boards are going to be expensive. So von Neumann architecture was the first one, right? Where the problem is, once again, von Neumann architecture suffer from the bottleneck, and the bottleneck is single path. That is the single bus which was available in the von Neumann architecture. So I think you got to go into these details, you got to learn about these details. Then in this we have talked about instruction execution, like how these units can come together to execute a particular instruction, an instruction which is just a mnemonic. So in order to understand the instruction, this thing may be just a starting point at this point of time, but unit block 3 talks about instructions in a much more elaborate manner, and block 4 gives you a very good example of instruction set, how an instruction set can look like. Okay. Then this unit, unit 1 and 2 also discuss the concept of interrupts. Now that is something very useful for every one of you to know. All the input output processing which you do from the keyboard, and you know the keyboard is one of the slowest device, right? So keyboard input output is with the help of interrupt. When you are dealing with the hard disk, interrupts are involved, although it is using direct memory access, but interrupts are only always involved. So interrupt is something like what we can simply assume that I am taking the lecture and somebody interrupts, okay, by raising hand and asking question. So that's a typical interrupt. So how the interrupts are going to be handled? Now typically if you ask a question to a particular teacher, teacher will not stop immediately, right? Teacher will stop at a point where he or she has finished a particular concept, and then he may come to you about your question. So that is how the interrupts are serviced in CPU by the CPU. CPU waits till the ongoing instruction is completed, and then the interrupts are acknowledged. And then there can be a priority of interrupts also, which one will be acknowledged first, which will be acknowledged later. For example, I mean, why priority is needed is, suppose a keyboard interrupt is being processed and there is suddenly a hard disk interrupt which occur at the same time. Then hard disk interrupt is going to be acknowledged immediately, and keyboard interrupt can wait. For the simple reason, because the hard disk interrupt, if it is not acknowledged immediately, then probably there will be a complete rotational delay, and if there is a rotational delay, you know, it may be in terms of milliseconds. So that is why the priority of interrupts also become very important, and there is a discussion on priority on interrupts. In addition, there are simple concepts like family of computer, then that is very large scale integration technologies. These are the things which has been discussed in these units. They are very good to know. Like today we are dealing with ultra large scale integration oriented technologies. Although if you don't know VLSI, then how you are going to understand the ULSI and all those kinds of technologies in a sense. But it is basically packing more and more logic into, I mean, it's gates, but then ultimately it is the logic, right? So it is the semiconductor technology which you are putting in, but ultimately you can pack more logic, you can pack more information, you can pack more memory within the CPU, you can build in more processor within the CPU. So all those things then fall from this particular information only. And the concept of family is one of the most important concept which was brought in by IBM. I mean, you learn from history, you remember that. Okay, so this is a typical concept about the family, where you learn a lot about how families, hierarchical things were transferred from various versions of families. Just like 8086, I mean x86 processor kind of things, where once again we are having the similar instruction set. So we have the similar kind of input output devices being used, right? So lot many good things are there as far as family. So you inherit a lot of good things from family, and over a period of time you you pack so many things that sometimes it becomes difficult to leave the bad things apart. So that also is a slight drawback, but that is where you will find that newer architecture also have come into existence, and one of that architecture happens to be the reduced instruction set computer architecture, which we might like to define a little bit later, but it has been discussed in one of the blocks of this particular course. Then there is a simple discussion about the fixed point, floating point arithmetic. Now what you need to understand is fixed point is very important, but then fixed point arithmetic represents a number range. For example, with 8-bit 2's complement notation, you can represent -128 to +127, and if you use 16-bit representation, okay, you will find the C programming. In C programming, the range is given from -32768 to +32768. So you just find out what is 2 to the power 15 and +1 value, and you will be able to relate. So -128 to +127, using the similar logic you can find out how various sizes of fixed point numbers are determined. So you should be able to know how various programming languages support those kinds of representation. Similarly, your ASCII, your UTF-8, UTF-16, all these coding terminology which you use in most of the data transmission stuff, including from when you are transmitting data from your device, like from your even input output device to the memory or to the computer, it is passed on as ASCII or UTF-8 or UTF-16 kind of a code. So that is another concept which you learn in this particular unit. And finally, there is a concept of error detection and other codes, which is a very important component to understand, because error detection is something which all of us should learn, how we can do error detection. Error detection is fine, the parity bit is fine. Okay, when do you, I mean, what is the importance of error detection and correction? Error detection is primarily when we transfer data from one source, a particular source, to a particular destination, right? So during the data transmission, if there is an error, right, that is what is to be determined through error detection code. And in general, in computer, 1-bit errors are detected, and if you want more bit errors to be detected, then there are complex codes. Okay, then wherever block level transmissions are there, then there are block level detection codes you will find in the hard disk configuration and so on and so forth. But for determining 1-bit error, you have parity bit, and for finding the error also, like which bit is in error, you then use the Hamming's error correction code, and then there is a double error detection code which can be done, which basically checks if there is an error in the 2 bits. So this is what we have covered in Unit 1 and Unit 2. Unit 3 and Unit 4 basically focus on gates and logic circuits. Unit 3 is primarily gates and logic circuits, the combinational and sequential circuits, and the sequential circuits are discussed in Unit 4, then design of combinational circuits and examples of combinational circuits. So this is where we have discussed about the Karnaug's map, and you should be comfortable with using K-map by now, because it's a very good visual representation of your truth table, and it is that is where you are able to find the adjacency and eliminate that adjacency. Like what you should be sure of, that each box in the Karnaugh map is representing a minterm. So by combining, you are combining several minterms together and producing an optimal solution. So that is how Karnaugh's map work in general, and it is a very useful tool for designing good circuits. All right. But there is a limit to visual representation. So Karnaugh's map can be used only up to when we have up to 6 variables only, and beyond that, then we have to go in for different kinds of methods. And one of the methods has been just introduced, which you may go through, and it is there over there. Then some of the combinational circuits like adders, decoders, multiplexer, read-only memory. Now these are some of the circuits. Adders we have discussed to a great extent when we were dealing with our sessions. Then decoder is primarily used when you are dealing with the decoder. It is basically selection lines are basically decoded lines only. So that is how you should be using the decoder to a great extent. Multiplexer is one of the important one, and you use it for register transfer and other shifting and all those kinds of things. So multiplexer, multiplexer in any case is one of the most important device. You multiplex basically from several inputs. There are multiple inputs and they are sharing one particular line. So how exactly which line will be transmitting onto that particular output line. So multiplexer is going to be one of the major device when you are constructing CPUs, when you are constructing exchanges of telephone or whatever, right? Because wherever sharing is there and multiple people are sharing less number of lines, you require multiplexer, right? Then read-only memory is one of the major stuff it is a combinational circuit, because read-only memory is fabricated, right? Whereas the read-write memory which you have, that is ROM is a sequential circuit because storage is there and then the changing of the value is required. However, in read-only memory, it is a simple combinational circuit, and whatever you want to store, you can store in the output, and just the line, you decode the line, and that's how the read-only memory can work. It can be utilized, ROM can be utilized for sometimes similar kind of ROMs can be used for fabricating your control units also. Right. Then we have flip-flop, which is a very important concept, like it is the storage unit, and there are sequential circuits like registers or shift registers which are utilized by various places. These are the things you learn. There are multiple programming, multiple instructions which you use shifting and all that, and the counter circuit which basically count the sequence. Then block 2 primarily focuses on the memory hierarchy, which I think we dealt with in a great detail in our session where we discussed about the cache, RAM, ROM. We not discussed that much, but DRAM, flash memory, all this information is available. Then we talked about a little bit of secondary storage technology and their characteristics. Then a very important device these days, this is the storage configuration, which is called redundant array of independent disk, RAID, and its levels. So it is organized into various levels. So what you have is a number of redundant arrays, number of disks, and how those disks can be used to store information redundantly. You see, whenever you want the enhancement, you want the enhancement of fast input output, okay, then you have to use redundant arrays or those kinds. But then in the redundant array, if you are getting fast input output, the advantage is fast input output as well as the that reliability of the storage system. Because why? Because reliability in the sense that there are 2 locations where data is stored. So even if one disk goes bad, you have the other disk available. But how that reliability is going to be built in, right? So that is one of the piece of information. And then what way, whether we can take simultaneous input output from those arrays, right? Array of disks. So that forms the basis of RAID architecture. So it is a very good architecture, supports, it's a very reliable architecture, and wherever the servers and all server farms are used, data centers, they all use somewhere down the line storage area networks or SAN, which basically RAID and all those things are utilized in those technologies. Then we have the memory system of microcomputer. So the microcomputer, we have typically the memory hierarchy, which includes the cache, which includes several level of cache nowadays, L1, L2. Then we have the main memory, then we have the secondary memory, and so on and so forth. Then input-output interfaces, which basically serial parallel communication interfaces which you have. Then you have these days you have many more interfaces available to video output, then HDMI. So those kinds of technologies are there. All those may not be discussed in the blog, but you can always refer to the material, take the help of internet and refer to internet-based material for input-output interfaces. The input-output interfaces, why they are very, very important? Because input-output interfaces communicates with the device on the one side, and they also communicate with the CPU onto other, or the system bus, like. So that is where they become very, very important. Why? Because the devices are very, very slow. So it is the input-output interface which has to control the level out the difference between the technology. So they are very important in that sense. And device controllers, device controllers primarily are input-output interfaces which has been implemented. So they are useful in SCSI, and those SCSI and IDE, etc. what you hear, they all are important stuff. Although on those interfaces you don't have to do much, but you should know what exactly those technologies are and why they are utilized. Then we have input-output techniques, and most of you are familiar with, we have dealt with the interrupt-driven input I/O and program-driven input-output. Then we have DMA and input-output processor, and then interrupt processing, like how interrupts are processed. So these are the concepts which has been discussed in quite a details as far as Unit 1 and Unit 2 are concerned. Then Unit 3 and 4 basically talks about the hard drive. They are primarily on the disk and the input-output technologies rather than anything else. So if you are dealing with the hard disk, what is partitioning, what is formatting, what is FAT, right? For file allocation table, which is a major part as far as your DOS-based, the Windows-based systems are concerned, how the files are allocated, how those things can be utilized. INODEs, which are used in Unix, FAT16, which used to be very common, now it has been changed. So you can, from there you can, from the starting point, you can always move to the latest technology in your own way, right? Then there is drive speed, access time, rotation speeds, which you deal with as far as hard disks are concerned, like how drive speed contribute to the access time. Okay, so that is how you have, and then hard drive interfaces, which you have is SCSI and the ID, which I just spoke about. Then removable storage options, you have many removable storage options, including pen drive and CD-ROM, DVD and all. And these days there is another very important input-output technology which you may be interested in is SSDs, solid state devices technology. The difference between SSD and hard drive, they technically share the same logic, but what SSD have an advantage that there are no moving parts. So all the information, it is all through the logical movement, and basically it is not the physical movement what you experience in the hard disk. So that is why the stuff where the SSDs are much faster and good interfaces, so they enhance the speed of input output to a great extent. Okay, and but they are expensive, right? Just like the memory hierarchy, the basic logic of memory hierarchy was itself that why memory hierarchy is difficult to deal with, because or why do we need a memory hierarchy, because it is difficult to invest too much in a single kind of memory. Although it will enhance the speed to a great extent, but it will increase the cost. And is it required? So there has to be a trade-off, right? So that trade-off comes in the form of memory hierarchy. So this is one trade-off, and the second trade-off is definitely the that the storage, permanence of storage and all other technology, the secondary storage technology offer you permanence of storage. SSD offers you between RAM and hard disk, somewhere in between kind of storage capacity as well as the speed. So that is a good option. In fact, SSD disks, when you use suppose you want to buy a new computer, then it may be a good idea to have some minimal level of, let's say, 256 GB SSD maybe, or even smaller SSD, and the operating system is onto the SSD and the rest of the data you have onto your hard disk. Even that is going to enhance your the processing speed, etc., to certain extent, to a great extent. So you can think about how exactly you can plan your devices, how exactly you can plan your systems. Okay. Then other devices which you have, video cards, liquid crystal display, right? So these LCD screens and all that which you use as an input-output device. So this unit talks about it. Modems, print resolution, scanners, keyboards, mouse, how do they work? I mean, it's not just what exactly they are, but how exactly they work, what are the scan codes, what is the print resolution, what is the scanner resolution, how does modem transmit. So some technical details are there as far as these units are concerned. Block 3 talks about the important part is the instruction format. Now instruction format, as you know, basically consists of the operation code and addressing modes and the actual address. So the addressing mode and actual address play a very important role when we are designing an instruction set. Okay, so that is what is the whole the aspects of block 3. So instruction format, the number of instruction which you choose for in a particular instruction set is very important. So the type of instructions which you want to get into a particular, which you want to have in an instruction set of a computer, which may be the arithmetic instruction, maybe logical instruction, maybe the shift instructions, then the program transfer control, the transfer of control instructions, and the special instructions. So these are in general the kind of instructions which you will be requiring in any kind of a computer, and all those has been discussed in this. An interesting thing has been talked about here is that how the number of addresses in an instruction, right, affect the size of the program. However, they also affect the size of the instruction. The more are the operand addresses, the longer is going to be an instruction. Now that is where some designer brought in a technology called reduced instruction set computers, where even if we are utilizing one or two operand in an instruction, even in that particular case, all the operands are in the register. All the operands are registered. So register operand, you got to have the smaller length addresses. But in the cases of some of the, it's as far as the machine goes, the data has to be stored somewhere in the memory ultimately, right? So those addresses are also very important, and they are also dealt with in reduced instruction set computers also. Then we have the type of operands over here. So number of the type of operand you already familiar with, which we discussed in the instruction, the representation of data, right? So that is where you can once again consolidate the type of operand which you have, that is floating point. If you are dealing with numbers, then floating point, fixed point. If you are dealing with characters, then you have ASCII, UTF-8 and all. And if you are dealing with the logical data, then there can be simple number representation for that also. Then there are addressing modes and their importance. And the addressing modes, as I talked about, the addressing modes many a times makes things easier for you to deal with. Specifically, one of the most important concepts which you use in your program is array, right? Without array, it becomes somewhat difficult when you are doing the repeated processing, right? So arrays are important, and to deal with array, you have typical that is indirect addressing modes, which require base address and all, base address with incrementation, decrementation. That makes the array processing very, very fast. You see, the organization has to go hand in hand with the programming languages. If it doesn't go hand in hand with programming languages, then what you will end up creating a machine which is not optimized for writing different kinds of programs. So that is what is important in this particular case, right? So description of, and then you always have registers. So this is what is important when we are dealing with, instruction sets. And instruction set architecture has one of the major role to play in a, you call a machine good or bad based on instruction set architecture to a certain extent. And the objective is to study what kind of programming environment this is going to be the best kind of a machine. So instruction set designer have many major role to deal with, and that is where I think the Intel designers have done great. I think they have done literally some good work, and that is why they are able to produce some wonderful processors, and which have been lasting from years to years to so many years it has been there. The Apple designers, I think now have moved on to, there is a convergence of as far as the technologies are concerned. So now we are having similar kind of architecture which are coming up for these machines, but still their overall instruction sets are somewhat different. Okay. Then the micro operation concept, this is very important, that how an instruction is going to be executed within the instruction. So an instruction is a macro instruction for a computer, right? For us, the programming language is a macro instruction, right? From programming language, then we convert to machine language, that there are a number of instructions which gets generated. And for CPU, even that machine instruction is a macro instruction, right? So that is how the thing goes, right? And that macro instruction requires certain steps of execution, where the simple, if you want to see the simple micro operations which will be required, some will be required for fetching. Now if for fetching, you will be, if I want to fetch an instruction, so there will be several steps which will be required. So each of those steps becomes a micro operation for fetch. Then the decode, for decode operation on the instruction will once again require several micro operation, and like that. So micro operation are the minutest or the smallest or the simplest kind of examples, the operations which are required for execution of the instruction, and those are basically at the level of, simply at the level of transfer of information, doing some arithmetic or logical operation onto the data, transferring data from one place to another, so that, it is something very close to how controls unit should be operating that particular computer. So somewhere down the line, micro operation leads to design of the control unit. Okay, so this is how the whole sequencing is there as far as design of the machine is concerned. So basically you have the application orientation, application programming languages, applications which are there. On that particular basis, the machine architecture is designed. And once the machine architecture has been decided, then on that particular, for example, if you are trying to work to let's say work in the area of neural networks and highly parallel processing oriented stuff, okay, weather forecasting and all those kinds of situation. So this von Neumann architecture is of absolutely no use to you. Why? Because the the bottleneck of one path, it makes it absolutely redundant, and you are dealing with one instruction is dealing with huge amount of data. So you require a different architecture altogether, right? So from your application, we design the instruction set, right? In fact, the programming language also can differ. So from programming language, then you define a very typical instruction set, the parallel instruction set or a serial instruction set or reduced instruction computer set. And from there, then you decide the micro operations which will be required to control the execution of an instruction, maybe the pipelining concept, which we'll be just discussing a little bit later. And then from there, then the final finally we move on to the design of the control unit, which is the unit which basically provides the control signal that now this operation is to be, micro operation is to be performed, this micro operation is to be performed. So that particular sequence can be preserved with the help of control unit. So it is all integrated, it's all related, and that is why they are coming in this particular sequence only in your block and your unit. So organization of arithmetic logic unit, I think that is what we have dealt with in the last session. So you should be familiar with the ALU and how ALU micro operations are designed. This is a very important stuff in that particular category. Design of simple units of ALU, arithmetic, logic and shift micro operation, as I told, we have already designed. Now the pipelining is a very interesting concept, because pipelining can be done for instruction, can be done for floating point addition, can be done for number crunching problem situation, but one of the most important pipeline deals with the instruction pipeline. So instruction pipeline is an interesting concept, because instruction can be divided into, like it is something like if I want to perform, for example, if I want to do railway reservation booking, all right. Now if I want to perform that particular task, how the things can be, one is that there is one person who is doing the reservation. So first person come, he does all the tasks of it, right. So that is first takes the form of it, then inputs all the data into the computer. Now at the next level, then collects the money, then issues the ticket. Now can we design a mechanism? Instead of one person, we have 3 parallel units which performs this particular task, right. So 3 workstations which will be performing, where one will be just collecting the form and just inputting your data. The second person will be specialized in reserving the ticket. The third person will be then taking the money from you, and the fourth person will be just issuing you the ticket in a parallel way. Now at the same time, 3 or 4 people will be in the queue and working into this particular pipeline. However, all these units are going to do small tasks. They can be specialized tasks, so they will enhance the speed, right. So they are the specialized tasks. So everybody is doing a special task. So you will be, that particular person will be mastering in that particular task. So like that. So that means in the computers, similarly, in a pipeline, the specialized task can be made more efficient, and then they move very, very fast into the units, and more instructions can be output at the same point of time. In fact, that is one of the pipeline is one of the hallmark of reduced instruction set computer, where one instruction per cycle is expected to be produced, which is a very good output rate as far as execution of instructions is concerned. Then this unit also, this block also deals with the hardwired control, as I discussed with you, that the micro operation leads to the control unit, and micro program control, where the concept like that is micro program memory, then how that micro programs or the micro instructions can be utilized by the control unit to issue different sets of signals. And finally, we have discussed about the RISC principle, where reduced instruction set computer has been designed, why they are needed. Everything in RISC happens to be very, very simple, and there are strong logic associated with reduced instruction set computer, specifically that in designing instruction set, we become very, very we become complex. We become complex in the sense that we try to build the complex instructions into the computer. Now, the result of that, bringing in complex, implementing complex instruction, is that simpler instruction execute at a slower rate, and that is not the essence. So what they say, that the complex instructions are hardly utilized by programmers, right. So it may be a better idea to enhance the processing of simpler instructions rather than enhancing the speed of complex instruction. So that logic they brought in with the help of what they did, some survey of lots of programs, and on that basis they came up with this particular idea. And they came up with that since the instruction formats are very simple, so all the register instructions should be there, the one addressing modes be very simple, all this simplicity was brought in. So when they brought in simplicity, they got a lot of space available in the processor, because with the VLSI kind of technology, a lot of complexity was being built into the logic, and that when the complexity was reduced, so a lot of space was saved, and they utilized it in creating many registers, and these registers are beautifully used for the passing control to next subroutines or functions. So that is the kind of discussion which has been dealt with in this particular unit. So this reduced instruction set computer helps in enhancing your modular design to a great extent. Like one function calling another, there is almost no movement is required as far as register transfer is concerned, but there is a movement of register window in RISC processor. So good philosophy, interesting philosophy, you will be enjoying it. And these days, remember, the processors are mostly RISC processors, so you must go through this particular concept in a great detail. It is a good, interesting concept. And then finally the RISC pipeline, which basically deals with that how instructions can be enhanced using the RISC processor. Then finally in block 4, we have discussed about the 8086 microprocessor. So 8086 microprocessor structure, which has 2 units, I think we have discussed in one of the sessions. Then the instructions related to 8086 microprocessor, the addressing modes related to 8086 processor, the type of instructions, the need and use of assembly language, why we should be using it. So all these things we have discussed. Input output in assembly language program with the help of interrupts. It's very important that how an interrupt can be, a software interrupt can be built into the system. So this assembly language program, we use interrupt 21H, not only to exit, but with different functions we can utilize for input and output. If you don't have microprocessor kit, there the different in and out instructions can be used in that particular kit also. But for the sake of assembly language instruction, it may be a good idea to deal with interrupt 21H with the different functions 01H, INAH and all that. So you will learn about these input output stuff from this block 4 in this particular thing. Then sample assembly programs have been provided. Some of them are using arrays, some of them are doing logical operations, some of them are doing transfer, right? One of the key problem which you will be facing is that first the logical concept you have to overcome is that there is a assembler directives. So, and assembler directives and segment registers. So, segment registers, why they are there, you need to understand that. Okay, segment registers are required just to convert a 16-bit address to 20-bit address, and they also divide logically memory into certain segments, overlapping segments, but that overlapping segment is not that important for you, but at least understanding that there will be a data segment, there will be a code segment, there will be a stack segment, and they should not, they can be overlapping in hardware as far as hardware is concerned, but in our implementation they should not overlap. For example, stack segment, suppose it overlaps the data segment, then probably there will be overwriting. So they should be separately stored into the memory as far as when you design it, and then how those segment registers are initialized. So for that, I think some of the instructions are there in the assembly language programming, and then the logical logic of assembly language programming. There are certain constraints, as you know, in assembly language programming, that in 8086 both the operands cannot be memory. Now if both the operands cannot be memory and you want to add 2 memory operands, right, then there is a problem, right? So you need to write longer programs, and dealing with arrays and other things you can do. Okay, one of the interesting thing about block 4 is the string matching. In fact, string matching is it's one kind of instruction which is not utilized by the compilers of the instruction. So string matching is a very interesting domain of instruction in 8086, and there are a few programs which are associated over there. Next thing which it talks about is the modular programming. Now, modular programming has been propagated to you in the form of structured programming from C, object-oriented programming, C++ and all that. So basically you are creating module with whether they are secure or not, that is a separate thing. But then somehow you divide your program into number of objects or number of modules or number of functions. So all these things need to interact, how they are passed on. So obviously there are going to be subroutine calls and return from those subroutine calls. Now when there are subroutine calls, what you are moving from a program. Suppose there is at one place is your program, then you move to a function which may be at a different memory location, and once that function executes, you come back. So that's how the subroutine calls one. So there is a like which is the next instruction to be executed, and then what is going to be the return value. So return values are always stored in the stack. Okay, so that is what has been discussed in modular programming. What has been discussed? There can be far function calls or subroutine calls or near subroutine calls. Near subroutine calls are within the same segment. So you only store the offset. Whereas when the assembly language there is a for assembly call, call, then you require to store the segment as well as the offset of the instruction. So like that, these kinds of information has been dealt with in quite a detail as far as modular programming is concerned. So then interfacing assembly with high level language has been dealt with. Now this really depends on compiler to compiler. So it has been dealt with, I mean it has been talked about in the context of C programmer, but it will be very difficult to implement because nowadays overall C program structure has changed, the models of C program has changed. So it will be difficult, but this is there just for an idea. Then a very interesting concept like device driver in assembly, how device driver can be designed, like what are the steps which are required for a device driver has been dealt with. And finally a very interesting program is there which is interrupts in assembly. Now the difference between an interrupt program and modular program is very simple. In interrupt program, what you do, you store the context of the machine also, because when you are doing modular programming, you know where exactly you come back and you know what is to be passed on and what is going to be returned, and none of the registers are impacted, technically speaking. And even if they are impacted, that is what you know, that has been the design of the situation. But when it comes to interrupts, in interrupts what we say the status of the program, whatever program which is going on, and we don't know which program is going on because interrupt can occur at any point of time of any when any program. So we don't know which program we are going to come back, and there is no specific call and return statement. Just there is an interrupt call to interrupt servicing program, right? So the status of the various registers is also stored when you are dealing with interrupt servicing, right? So when you are writing an interrupt servicing program, all the registers which might be affected by the interrupt servicing program need to be stored. Once again, where are they going to be stored? Always onto the stack. There is no other, there is no third place where the information is stored. It is always stored onto the stack, and then the information is, the interrupt service program deals with all the things. Then the returns to the next instruction, but storing the context, restoring all the registers once again. So that is a very interesting, and there is one very good program where you will find how stack, where exactly will be the return address, how the addresses of various registers will, where exactly will be the addresses of various registers, how they will be saved, how they will be restored. So that kind of information is there. So you will, I think you will really like that particular example if you know this particular context about it. So this in general is the overall structure of MCS 012, which is a course on computer organization and assembly language programming. There are many activities which you can perform onto this particular course, which deals with that studying the block is the most essential, but then you can always learn from external sources, and there are 3 references which are given in the block. You can always refer to those references if you want to learn more. Then you must solve all the check your progress questions by yourself, compare your answers with the whatever has been given in the block. Okay, then solve different assignment questions you will in the context. So basically assignment questions, like learning is very interesting domain where you just don't learn by just studying. Okay, you also learn, I mean you retain maximum of learning if you perform some problem solving also along with it, right. So that is why we want you to solve these assignment questions which are primarily either analysis type or some of them may be recall, but very few are of the recall type. Many of them are analysis, compare, contrast, understand and explain, basically explaining the things may make you good in particular presentation skills. And then there are many problem solving oriented also, where we ask you several questions where you solve different problems in your own way, which may be slightly different from what is given in the block. So that enhances makes the learning permanent. You can also do questions from the previous year question papers, especially the numerical questions, right. They will be helping you your understanding, and also give emphasis to theory question and try to write your answer and then compare with whatever is given in the block and unit, what points you have missed and so on and so forth. And you have any problem, you are always welcome to discuss with us. Just one piece of information, that assignment carries 25% of the weightage and Viva voce is compulsory in the assignments. So make sure that you do your assignment yourself, because although Viva voce counts 20% weightage only, but if somebody fails in Viva, then his or her assignment will be marked at a very, very low level. So you prepare well, you do well in your assignments. The last date is very nearby, but be thorough with your assignments. I mean, after writing the assignments, I mean, it is always a good practice to go through it, I mean go through it again, and if you need to write it again, there is nothing wrong in writing it again if there are too many mistakes, right, because it always helps. If you are writing it again, it always helps you in that particular sense. Okay, thank you so much, and I think I am signing off from this particular course. Thanks and bye.